In this lesson, we will look at how we can use the first derivative and the second derivative to sketch the graph of a function. But before we sketch the graph of a function, let us first look at the following terminologies. First is the domain. The domain is the set of all permissible values for x. So if your function is like a polynomial function, then your domain would be any real number. If your function is, say, a square root function, so say square root of x, it means that your x values here should be greater than or equal to 0. So there is a condition. In the same manner that if your function contains, say, 1 over x, a variable x in the denominator, then you know that x cannot be equal to 0. Okay? So domain is the set of all permissible x values. And then we will look at the intervals where the function is either increasing or decreasing. So for increasing or decreasing intervals, we will look at the first derivative. Because remember, the slope of the line, slope of the tangent line is basically the first derivative of the function. So if the slope is positive, the first derivative is positive, then that means that the graph is increasing on that particular interval. And if the slope is negative, so your graph is going down, all right, or the first derivative is negative, then the function is decreasing in that particular interval. And then we have the relative maximum. So the relative maximum, or also called the local maximum, okay, is a point where the first derivative changes from positive to negative. So say, for example, we have a portion of the graph looking like this, okay? So the slope right here is positive, okay? And then the slope here is negative. So the first derivative changes from positive to negative. That point is the maximum point, relative maximum point, or the local maximum point. In the same manner that you have a relative minimum if the first derivative changes from negative to positive. So from negative to positive. So in this particular portion of the graph, the slope is negative. Okay, first derivative is negative. And here the first derivative is positive. So that point, that is our relative minimum or local minimum, meaning it's a lower point in the graph. Okay. Next, we have concave up or concave down. So concave up is valleys. Okay, just like the valley in between the two mountains. Okay, it's the lowest point in the graph. So in other words, if you have a relative minimum, then that means that the function is concave up at that point. Okay, it holds water. That's your concave up. Okay, it can hold water. Okay, and to identify the concavity, we use the second derivative. So if the second derivative is positive, then the graph is concave up at that interval. On the other hand, if the second derivative is negative, then your graph at that interval is concave down. Okay. And then we have what we call the point of inflection. The point of inflection is a point on the graph where the graph changes concavity. So say, for example, we have this graph right here, okay? So from this interval to here, okay, notice that the curve is concave down, right? Concave down. And then from this point onwards, the graph is concave up. So there was a change in concavity. Now the point where that concavity changes, that is our point of inflection. Okay, so You have a point of inflection if the second derivative changes sign, either from positive to negative or from negative to positive. Okay? So bear in mind this vocabulary because we will be using this a lot. Okay, let's take a look at the following. So we are given this graph. Okay, we don't know what the equation of this graph is, what the function is. Let's call it y equals f of x. Okay, and we are given different x values at each point in the graph. So we want to identify first what the domain is. Now remember, the domain is all values for x. And by the way, you have an arrow at both endpoints. So that means it goes on indefinitely. So since it goes on indefinitely, and notice that the graph is continuous, then we say that the domain is all real numbers or all reals. Okay, and if you want to express this as an interval, then we say the domain is from negative infinity to positive infinity. Okay, now let's read the graph from left to right. So from negative infinity, you have a negative infinity here. So from negative infinity to A, okay, negative infinity to A, your graph is decreasing, right? It's decreasing, it's going down. So from negative infinity to point A, and when you write down the interval for increasing or decreasing, we always use parentheses. So from negative infinity to A, the graph is decreasing. And then from A to B, the graph is increasing. So from A to B, the graph is increasing. This is not an ordered pair. This is your interval notation. And then from B to C, the graph is also increasing. So it's not only from A to B, but from A to C, the graph is increasing. Okay. And then from C to E, look, from C to E, your graph is decreasing again. So from C to E, the graph is decreasing again. And then from E to infinity, the graph is increasing. Okay. Now, usually we put U for the union. Okay, meaning it is a combination. So it's increasing from A to C or from E to infinity, and decreasing from negative infinity to A or from C to E. Okay, now let's take a look at the maximum, relative maximum. Now there is no absolute maximum here. We do not know what the maximum point really is, but within the graph, we have this high point, right? So within this interval, okay, within this interval, we have a hilltop right here, which is at point C. So you have a relative maximum when X is equal to C. And then we have a minimum right here. Okay, a low value here, you have a valley. And then another one right here. Okay, so we say we have relative minimum at X equals A and at X equals E. At X equals A and at X equals E. Okay. Next, we have concave up. So concave up is the cup, right? It holds water. So concave up would be from negative infinity to B, okay? So from negative infinity to B, and then from B to D, that would be concave down, right? So you have concave up, concave down from B to D, and then another concave up from D to infinity. And then again, we use that U, union. from D to infinity. Okay. Next, we want to find the point of inflection. Remember, point of inflection is where the graph changes from concavity, right? So from negative infinity to D, it's concave up. Then B to D, it's concave down. So there is a change in concavity at point D. So X equals D is a point of inflection. And then this is concave down from B to D. And then from D to infinity, it becomes concave up. So concave down to concave up, that change happens at X is equal to D. Okay.